Hello everyone, I am Sanjeev and I welcome all of you to Searching AI, and this is lecture 4 for the course ARL 1011. So the topic for today's presentation is kernel methods in reinforcement learning, and this lecture is specifically focused on the Ronald Parr's publication Kernelized value function approximation for reinforcement learning. And in the next lecture I will show an extension of this algorithm to the control problems. There is this kernelized state action value function approximation for reinforcement learning. So this lecture will first introduce you to the kernel methods for the least square regression. There is a dual representation of the least square regression problem. Then I will introduce you to the Markov reward process. So the order is changed. First I will introduce you to the Markov reward process. Then I will introduce you to the kernel methods for least square regression. This is a dual representation, and then the main algorithm of the publication. So here comes the Markov decision process. So a Markov decision process is a 5-tuple which is defined as S, A, P, R and gamma, where S is a set of all states or the state space, A is a set of all actions that the agent can take in a given state, P is a Markovian transition model or the stochastic transition matrix whose components P, A, S prime gives the probability of making a transition to state S prime when agent takes the action A in state S. R is a reward function whose components are S, A, S prime gives R, A, S prime. There is an immediate reward received by the agent when it takes action A in state S and makes a transition to state S prime, and gamma is a discount factor. So a Markov reward process, if we use a constant policy for the Markov decision process, then it will result into the Markov reward process, and Markov reward process is defined as S, P, R and gamma. There is a 4-tuple where as a set of all states, the components of matrix, the components of P, that is Pij, represents the probability of making a transition to state Sj from state Si, and R, capital R is a reward function whose components Ri is expected reward, and gamma is as usual the discount factor. So the target of the algorithm kernelized value function approximation is basically to solve the prediction problem. Remember, it is not solving the control problem, that is, it is trying to compute the state value function and not the state action value function. So the target is to find the value function, that is a state value function V, which is the mapping from states to the expected discounted total reward for the process. This is a Markov reward process. So the value function, state value function, is a mapping from states to a real number. There is a rewards. There is the expected discounted total reward the agent can receive starting from state S. And the optimal value function satisfies this satisfies the Bellman equation. There is a V star. The optimal value function is equal to R plus gamma times P times V star. But the value function is written in the matrix format, and you can refer to the previous lectures to derive this equation. So here's the first important part of the lecture, that is the kernel trick for solving the least square regularized least square regression problem. Regularized least square regression and regularized least square regression are pretty simple problems, and they both have the analytical solution. However, here we will discuss the dual representation of the regularized least square problem, and we will analyze the kernels, the kernels and the kernel methods to solve the regularized least square problem. The whole paper, the kernelized value function approximation, is based on the regression, that is a kernel regression, and therefore we will analyze the regularized least square regression, its dual representation, which introduces the kernels. So the problem is pretty simple. It's just the minimize with respect to the weight vector w, erw, where er denotes the error function and er is defined as sum over all training instances. There are n training instances defined by xn comma yn, where yn is a target value. Here phi is a feature vector which maps the training instances xi's to the vector in Rk, and w is a weight vector which assigns the weight to each of the basis function. So w transpose times phi of xn minus yn is the error over the training instance xn comma yn, and likewise we sum over all training instances. We take the square of the error and then we add the regularization term, that is a w transpose w, and lambda is a trade-off parameter, is a positive trade-off parameter, and therefore this problem is a bi-criterion problem. So a simple regularization problem, this is a very simple regularization problem and very easily solvable with an analytical solution. You can just differentiate this equation with respect to w and equate it to 0, and then you will get the analytical solution for the weight vector w. So let's analyze the kernel method. There is a dual representation. So the first thing that we'll do is to differentiate this objective function, that is the erw. There's an error with respect to w, and on differentiating it we get this expression, that is the differentiation of this error function with respect to w is just half of sum over all n, sum over all training instances, del over del w of w transpose phi xn minus yn square plus lambda over 2 times del over del w of phi of w transpose w. So why are we differentiating it? So the first thing is that the objective function is convex function. So differentiating the objective function and equating it to 0 will give the solution for the weight vector w, for which the error is minimized. Since this is a convex function, therefore on differentiating with respect to w and setting the expression to 0 will give the solution for the w such that the error is minimized. So the first term is w transpose phi xn minus yn squared, and since this is a square function, this is a convex function of w, and therefore sum over all such training instances is basically the sum of all convex functions, and therefore the first term, that is half of sum over all n w transpose phi xn minus yn squared is a convex function. So this whole term, the first function, is a convex function since it is a sum of convex functions, and therefore it is convex. The second term or the second function is lambda over 2 times w transpose w. Now w transpose w is a square, it's just a square of the weight vector w. Think it as a scalar term. Suppose you have a scalar x, and then the x square will be a convex function, and therefore w transpose w is a convex function, and lambda is a positive parameter. So lambda is positive, therefore this whole expression is a sum of the convex functions, and therefore this whole objective function is a convex function. Since it is sum of the convex functions, therefore the whole objective is a convex function, and therefore on differentiating this convex function with respect to the weight vector w and setting it to 0 will give the solution for the w for which the error is minimized. Therefore, as I said, that objective is convex quadratic function of w, and therefore to obtain the minimum we will differentiate the error function with respect to w and we'll set it to 0. So here's a exact mathematical expression for the differentiation of the error function with respect to w, and it can be skipped if you're not interested into the exact mathematical expressions. So this is the expression for the differentiation of the error function. There's half of sum over all n from 1 to n del over del w of w transpose phi xn minus yn squared plus lambda over 2 del over del w of w transpose w. So differentiation of this expression is twice of w transpose phi xn minus yn times phi xn plus lambda over 2 times 2w, and this will cancel out, and likewise here this 2 will cancel out, and we'll get the expression for the differentiation, that is sum over all n, that is sum over n from 1 to n w transpose phi xn minus yn times phi xn plus lambda times w. You can refer to the first lecture in machine learning channel of Searching AI, that is the linear regression, and there I have explained the differentiation rules, that is how to differentiate w transpose w with respect to w, and how to differentiate this expression, and the results of differentiating such as x transpose ax with respect to x, it will give you just 2ax. So all these results of the differentiation I have explained in the first lecture of machine learning channel of Searching AI. So you can go back to that lecture to understand all these rules of differentiation. So finally we will set this expression to 0, and it will give us the solution for the weight vector w, that is negative 1 over lambda times sum over n from 1 to n w transpose phi of xn minus yn times phi of xn. And now we will use this solution for the w to derive the dual representation. So using this representation, the vector mu for representing w transpose phi xi minus yi, and using the matrix phi, there's a design matrix phi whose ith row is given by phi xi transpose. We can write the solution for the w in a matrix form, which is given as w is phi transpose mu, where phi is again the design matrix whose ith row is given as phi xi transpose. So phi is an n cross k matrix, and mu is a vector in Rn. So using this representation for w, we can derive the kernel based solution. There's a dual representation for the regularized least square problems. Expanding the error function gives us this expression, half of phi times w minus y transpose phi times w minus y plus lambda over 2 w transpose w, where y is a vector whose components are given as y1 to yn. There is a set of all target variables. So on expanding this term, phi times w minus y transpose phi times w minus y gives us this expression, w transpose phi w minus twice of w transpose phi transpose y plus y transpose y plus lambda over 2 times w transpose w. So substituting the solution for w is phi transpose nu and the error function will give us the error function in terms of the vector nu, which is given as half of nu transpose phi times phi transpose nu minus twice of nu transpose phi times phi transpose y plus y transpose y plus lambda over 2 nu transpose phi times phi transpose nu. And now we define the Gram matrix, which is defined as phi times phi transpose. This Gram matrix is basically the kernel matrix, which is an n cross n symmetric matrix whose components k ij is given as phi xi transpose phi xj, and we represent the component kij, the ij component as k of xi comma xj, which is defined as phi xi transpose phi xj. So basically the gram matrix k is the kernel matrix, and in the kernelized value function approximation algorithm we will see that this kernel matrix can be any matrix. This is not restricted to just phi transpose phi. It can be a Gaussian kernel, it can be a Laplacian kernel, it can be any kind of kernel, any valid kernel. So substituting k for phi times phi transpose will give this equation for the error function. It's half of nu transpose k times k nu minus twice of nu transpose ky plus y transpose y plus lambda over 2 nu transpose k nu. So again this expression can be analyzed. This is a convex function, that is a convex quadratic function with respect to the vector nu, and therefore on differentiating this expression with respect to the vector nu and the setting the resulting expression to 0 will give us the value of nu for which the error is minimized. So differentiating the error function with respect to nu and setting it to 0 and using the property that k is k transpose, since k is symmetric matrix, will give us the solution nu is equals to k plus lambda I inverse y, where I is an identity matrix of appropriate dimension. So this is an analytical solution for the vector nu in terms of the kernel matrix or the ground matrix k, and this is known as a dual representation of the regularized least square problems. So for any new instance x, the target value y is basically phi x transpose w, which is given as phi x transpose phi transpose nu, substituting the value for w, that is phi transpose nu. So substituting this we get phi of x transpose phi transpose nu, which gives phi of x transpose phi transpose k plus lambda inverse times y, where y is a vector representing the target values of all the training instances. So expression for nu, we substitute this expression here, will give us this expression phi of x transpose phi transpose k plus lambda inverse times y, and representing this again with the kernel will give us k of x transpose k plus lambda inverse times y, where k of x is a vector in Rn whose nth component is given as k of xn comma x, which is phi of xn transpose phi x, where xn, these n components represent the n training examples used for determining the solution for the vector nu. So the nth component is given as phi of xn transpose phi x, which is represented as k of xn comma x. So this is the dual representation, that is for the new instance x, its target value is given as y of x is equals to k of x transpose k plus lambda inverse times y. And here's the important thing about this solution: this lambda times I accounts for the regularization. If we remove this lambda I, then, or if we put the lambda equal to 0, then we will get the solution for the unregularized linear regression. So the dual formulation allows a simple least square problem to be expressed in the kernel form, and hence we can utilize the power of the kernel trick. So here are some facts about the kernelized value function approximation algorithm. So the first thing is that the algorithm exploits the kernel trick. That's why we have discussed the regularized kernel regularized least square problem and its dual representation. And the second thing is that it is a model based method. It is used for prediction problems, that is not for the control problem. It computes the value function for the states and not the state action value function. So as I mentioned, this in the dual formulation, the matrix lambda I in the solution accounts for the regularization, that is the term lambda over 2 times W transpose W results in this matrix lambda times I. The lambda is a scalar, positive scalar, and I is an identity matrix of appropriate dimension. So we will use the notation sigma, which represents the lambda times I, and in the algorithm is the kernelized value function approximation. The sigma is not restricted to a diagonal matrix, that is, it can have the non-diagonal elements as well. So here are the three main important things about this algorithm. The first one is that the algorithm uses the kernel based regression approach to estimate the reward for each states, that is, it tries to estimate the reward for the state, that is, the S state is an input vector and R is a target vector. This is the analogous interpretation to the least square problem, where X is a input and Y is a target for this X. Likewise, here in this algorithm, the R can be considered as a target variable and S can be considered as an input variable. So we are trying to find a relation between the states and the rewards. The second thing is that it tries to predict the kernel values k s prime, and it does this by using the kernel regression model, and we will see this what k of s prime is when we discuss this. And the third thing is that the algorithm exploits the fact that the value function is sum of the gamma discounted feature rewards. Obviously this is not to mention, but here it is stated explicitly so that it will help in understanding the algorithm. So now let us represent all the three facts in the mathematical terms. So the first one is that the algorithm tries to find the relation between the states and the rewards. So the reward for, or the expected reward for a state S is given by k of S transpose times k inverse times R, where the solution is obtained from the regression model for the unregularized regression model, and for the regularization case it is k of S transpose k plus sigma inverse R, where again S can be interpreted as the input and R can be interpreted as the outcome or the target value. So for a state S, the expected reward for this state is given as k of S transpose times k inverse R, where R is a vector formed from the samples, that is, the first step is to collect the samples and then the sample rewards are used to form this vector, and this k of S is given by this expression k of X. Here k of X is basically phi of xn transpose phi x, where xn represents the training instances, the instances used for finding the solution for the vector nu, and likewise for k of S this would be phi of Sn transpose phi s, where phi of Sn, the Sn is are the sampled states that were used to find the solution for the weight vector nu. And therefore the expected reward for the unregularized case is given as k of S transpose k inverse R, and for the regularized model it is given as k of S transpose k plus sigma inverse or times R, where this matrix K is defined as the kernel matrix whose components I, J are given as Si, k of Si, Sj, which is defined as phi Si transpose phi Sj. The second fact is that it tries to predict the kernel values k of S prime, and therefore the k of S prime using the regression model is then given by k of S prime is ks times k inverse times k prime, where K prime is basically the P times K, where P is a stochastic transition matrix, or the transition matrix whose components give the probability of making transition from state Si to state Sj. So the I comma j component of this matrix K prime are given by expected value of K of Si prime comma Sj. So using the regression model, K of S prime is given as Ks times K inverse times K prime. And this is a regularized version of the state prediction model. There is K of S prime is Ks times K plus sigma P inverse times K prime. And the third fact is that the algorithm expresses the fact that the value function is sum of the gamma discounted future rewards. So the value function for state S is given as the R1, that is the immediate reward when agent makes a transition from state S to next state S prime, and plus the gamma times reward R2, that is a reward received when making transition from S prime to the next state, that is the S double prime, and likewise the future discounted rewards. So V of S is given as R1 plus gamma times R2 plus gamma square times R3, where future rewards are discounted by gamma. And using the kernel models for the rewards, we get this expression for the unregularized case, K of S transpose K inverse R, where R is the reward for the state S, which is given as K of S transpose K inverse R. So the R1, that is the reward for state S, is given as K of S transpose K inverse R, and for state S prime it is again given as K of S prime times K inverse R, where K of S prime is given by this expression K of S times K inverse K prime for the unregularized case, and likewise we do this for the future states. So finally the value function is given as K of S transpose sum over I from 0 to infinity gamma I times K inverse times K prime to the power I times K inverse R, and this is the sum of infinite GP, or the geometric progression, whose solution is given by this expression K of S transpose times I minus gamma times K inverse times K prime inverse times K inverse R, and moving this K inverse inside this will give us this solution. There is a value function for state S, or the value of state S is given as K of S transpose times K minus gamma times K prime inverse times R, where again the K is a kernel matrix. The K prime is P times K, the matrix K, and R is a vector, is a column vector formed from the sample rewards. So this is a solution when we are using no regularization term, that is the unregularized solution, and the regularized solution is easily derivable. Just follow the same steps and use the regression term, that is a sigma, and by doing so we can get the value function for the regularized case. So I'm not showing any practical application of this algorithm, and I will show the application of the next algorithm, that is a kernelized value function, the kernelized state action value function approximation in the chain domain. I will discuss this algorithm in the next lecture. So as I have mentioned, I will show the working of the extension of this algorithm, which I had developed for state action value function, in the next lecture, along with the downloadable MATLAB code. So thanks for watching this lecture.